Hello everyone, we are the Team 4. Qatar National Museum is a national museum located in Doha, Qatar. The museum was opened to the public on March 28, 2019. Built at the site of Qatar National Museum and designed by architect John Newell. The building was inspired by the Desert Rose Qatar Fort in Qatar. The new Qatar National Museum is located in Museum Park Street in Doha, Qatar. The total building area of the project is nearly 40,000 square meters, providing 8,000 square meters of the permanent expansion space and 2,000 square meters of temporary expansion space. It also includes an artificial lagoon and 400 car parking space, a research center, a laboratory, a 70-seat conference room, a 220-seat auditorium, 2 restaurants, a cafeteria, storage facility, and museum stores. Inspired by the mineral structure Desert Rose, the rock crystallized from the clump of earth beneath the surface of the shallow side basin. A series of interlocking discs surrounding the History Palace. The exhibition space is fan-shaped and surrounds the central garden halls where outdoor control events can be held. Its desert rose shape reminds us of Qatar culture and climate. It rises from the grass and fuses with the earth. Exposure allows visitors to walk outdoors while protecting the interior from the sun. The sand-colored concrete cladding harmonizes with the local environment. About BM model and the sequencing of design. Interior envelope showing a total of CA 600 discus objects, and close-up showing the SSS on the primary steel structure, and detail of main structure, SSS and the fixing beam in the interface to the FRC panels. Primary steel structure map concrete fender XO2 union, and the intersection of adjacent discs. The building envelope consists largely of double-covered FRC panels. These panels are attached to an adjustable secondary steel structure. This secondary structure in turn is located over the roof skin with a substructure made of trapezoidal sheet metal. Foam glass insulation glued over the entire surface, and the bitumen roof seal. The FRC panels largely have an individual geometry, adjustable stubs with the well-done bolts from the interface between the polygonal primary steel structure and the curved SSS girders, which precisely follow the three-dimensional spherical cap geometry of the discs. Insulation and waterproofing is done around the stub. Its surface precisely follows the individual curvature of the respective discs. For this purpose, high-precision CNC computer-milled 3D formwork sets were concrete from styrofoam. The finished panels were brought to the construction site in special transport frames. The structural design of the tender was carried out by the rule based on the Tackler software system to rationalize the main steel structure. A standardized transport structure system was designed to provide radial alignment for a larger transverse roof discs and orthogonal alignment of supports and beam of smaller vertical discs. Due to seemingly random geometry arrangement, individual disc segments are often superimposed. The structure of the building includes a number of intersecting steel film discs, thus creating many connections between discs of different geometrical shapes. Many customized connections are avoidable. A significant number of connecting CHSs can accommodate a large number of incoming member arrays, thus standardize the supporting steel arrays. To communicate this information to the contractor, a number of connections have been designed and detailed on drawing with 3D perspective and 2D sections. The properties of each connection point are important because it is impossible to accurately understand geometry and design without the question of three-dimensional intersection. Axis lines of 250,000 steel frame profiles are parametrically generated on the real software system based on the structurally determined out surface and calculated as FAM. The steel reinforcement information and foundation of 1,600 splined piles was transferred to the technical model to form the basis of building along with the steel structure detailed 2D drawings. Engineers gradually added the necessary connection details to the model so that Tekla 3D data can be used directly to produce drawing, manufacturing, and interdisciplinary design, coordination of advanced BIM models points. A total of 130 lanes of discs was used to building the museum ceilings, slabs, and walls. This spherical cross-section vary in diameter and curvature, with radius ranging from 10 meters to 53 meters. There are two types, ceiling and vertical, which can be adjusted to the lower and lower planes by means of beams of light beams. The vertical disc is the support of the project and traverses the remaining load from the horizontal plane to the base. These discs are formed by the radial steel reinforced structure with a waterproof envelope. In the gap between them, spectacles appeared, embedded at the far end, and from the outside. They seem to have no frame. The space in the building is formed by the space between these discs. The structural design of the tender was carried out by a rule-based of the Tekla software system to rationalize the main steel structure. The standardized transport structure system was designed to provide radial alignment for larger transfers, roof discs of a single alignment of supports and beam of smaller vertical discs. Due to similar random geometry arrangements, individual disc segments are often superimposed. Therefore, in order to accurately record the entire load transfer, a large fraction of the model must be fully calculated. Support structures are made of steel structure called primary steel structures. The link between the primary and secondary steel structure supporting the sandwich is circled with bolts. These codes control the geometry of the curve's length and feature an internal circular line. The secondary structure consists of steel sections. They are curved, so they are consistent with the fixation of axially symmetrical concrete sheet. Secondary steel structure consists of beams that are simple to support and have maximum distance of 3 meters. They are painted to the limbs. One normal, the hole the other one, is a rectangular hole. The concept of tessellation of one line is illustrated as finger, with radius of 31 meters. The panels are arranged such that a limited number of around 20 different panels elements and 2 nose elements cover the entire area of the lines with a simple rotation. In order to cover the entire surface of the museum, there are around 150 different panels according to the lens curvature. This system was chosen in order to limit the number of molds for the panel's fabrication. Depending on the molding location or type of panel, these so-called fasteners have been developed as the point nose panel for use with normal case and discus edges. After panel alignment and fitment, seal the joint with a permanently elastic silicone sprinkled with sand. Figure shows the impression of the construction process. Some images convey a sense of the inmost sense and geometric complexity of project, which is the special challenge of everyone involved. The goal is developed very different interfaces and a geometric intersection into a continuous and optimized substructure, which a silicon joint is placed as illustrated. The silicon joint is white. After silicon application, fine calcine is poured over the surface of the joint. The cladding system is composed of the following layers of illustrated rib deck fixed on the primary steel structure, in solution and waterproof membrane supported by the rib deck, and studs welded on the primary steel structure, and secondary steel structure supported by the studs. Concrete cladding fixed on the secondary steel structures. Construction size and supervision of execution in addition to the conception and planning of the building shell. The scope of services provided by WSS also includes the supervision of the team of architects and engineers who were present on the construction site at all times. This team was responsible for supervising the construction site during critical assembly processes, clarifying the interfaces, coordination, and last but not least, communicating the planning to the local contractors. The construction site required a highly sophisticated delivery and warehousing systems. Among other things, 12 large tower cranes and countless mobile cannons was used. At peak time, up to 3,500 workers and 300 architects and engineers were working on the construction site. This outstanding architectural vision could only be caused reality thanks to the ongoing and highly professional commitment of everyone involved and the most modern planning and construction technology.